Hi everyone, I'm Rithwik, Product Manager at Arca Energy, and today I'm here with Ankit, our ML engineer. We are here to talk about our AI roof product. This product we have built specifically for solar companies who are designing, selling, and installing rooftop solar. This particular feature is built to help these companies reduce their PV design time from 15 minutes to 15 seconds. Before we get into how we built the feature, let me just spend a couple of minutes on what is the exact problem we're trying to solve. Until now, for solar companies to install a PV solar, they had to draw a 3D layout of the house. And especially for drawing pitched roofs which have multiple roof faces, the designers need to be skilled in CAD. Though we solved that problem by introducing the Arca 360 platform, which made it easier and intuitive for any designer to draw a 3D roof, it still typically took them 15 to 20 minutes. And when you're dealing with hundreds of leads, this becomes a bottleneck. So our main goal for this product was to remove that bottleneck and increase the number of proposals and PV designs any designer could solve. So Ankit, can you please take us through how we built the feature?
Yeah, sure. Hi. This feature, basically, it was mainly aimed to solve the main problem for the design. So that is, in solar design, roof modeling is still very manual, and the designers have to trace the roofs, understand the geometry, and build 3D models by hand. So it takes time, and it's repetitive, and it does not scale well. So we built an AI system that automatically detects the roof from the satellite imagery inside the software itself, and understands the structure and feeds it to the AI pipeline, and then generates a 3D generation of the model. So from a user point of view, they'll just upload an image, and the user will be able to get the roof much more faster than he thinks he will be able to design. So the input times minimizes to seconds from minutes, and this was built by a team of 5 of us. So across the ML backend and 3D backgrounds. So my role was mainly leading the ML side of the system, and then integrating that to the 3D model.
Got it. And this is not a research project. We have actually pushed into production, and there are multiple solar companies currently using it. So let's talk about the nitty-gritties of it. Starting from model selection, the data selection strategy, how was the training set like? Can you take us through the start of the project and how it has progressed over the time?
Sure. So from day one, we treated this as a production feature. So this meant choosing models that were stable, fast, and maintainable, and not just accurate on paper. So we experiment with multiple models that included Ultralytics YOLO V8, V9, and also V11 models. So we experimented with multiple models to understand the trade-offs, but YOLO V8N, the nano model, was fast, but it kind of struggled with complex roofs, right? And then we tried the medium model for V8, and it still gave us a better accuracy, but there was some stability issue with that. So again, we tried with V11. So we tried a number of iterations to finalize our final model. And as we went ahead, we were closely tracking the many features and metrics like the loss curves, precision recall, and mainly the MAP 50 and 95 values. So some models did better, like V8, and some were lagging behind. So we did many of the classifications for these iterations, and then we found that the V8 model, right, it is quite better than others. So we finalized this V8 model, and then we turned around to think about the dataset, because that was the next main thing to get ahead.
Yeah, when you say some models perform better than the other, can you tell us what are the exact metrics that we're tracking to compare between models?
Mainly we were tracking the IOU values, and also the main MAP values 50 to 95, and also the MAP 50. So as we began to iterate with YOLO V9 and V11, so we saw that those results were not that satisfactory as we got from the first training, right? So the main thing was the dataset that we chose. The first dataset, that was around 60K images, right? And because of that data being vast, right, and having distributed amount of classes, like, and in different dimensions we have captured the images and the structure and annotations also. So those helped us to like get a better model than these like V11 and V9 models, but still they were like kind of good. But again, then we turned back and we saw the hyperparameter section. So as we tuned them, right, and also we introduced the tuning of the models to stop at the proper epoch and then avoid overfitting and underfitting. So this really helped us to get different models out of it. So we thought V8 is the best one that will get us the good model. So we then turned on to like minimize the data set. To get a 35K data set, I think we took a month, and our internal team worked really hard on that to get the noise data out. And then we landed out with 35K data set, and then we got a V8N model out of it, which was very excellent performance. So the metrics they showed around 50 to 20% of improvement, talking about the precision, recall, and the MAP values. So MAP values were straight around 25% higher. So these metrics helped us to understand the model better and then choose the V8 as the production model.
So you talked about three things here. First, let's set that the metrics that you're talking is IOU and MAP. So IOU was intersection of tuning. You're just trying to measure with the actual data set, is the model able to rightly predict the exact roof is as it is or not? And when you say MAP values, you're trying to see if the ML model is actually trying to identify if there is a roof exactly in that image or not, right? So these are the two things you're practically tracking.
Okay. Yeah, so MAP basically lies on the basic two component, that is precision and recall. So as these values are properly tuned, so the MAP value will increase properly and decrease accordingly if the model is properly tuned and everything. So we saw a gradual increase in this. So we tried to shift the data set down to 35 because we removed those noises, and we really saw that the results are very good and we got better accuracy to the models.
Yeah.
So this is how we concluded for the V8.
Got it. So yeah, the second is regarding data set. You had a larger data set to work with to do the initial training part, but you have seen that the noisiness of the data was actually deterrent than the actual size. So when you actually scaled it down to a 15K and then increased to 35K, you saw a drastic increase in the model size. I think you mentioned numbers of the precision went up from 74 to 90% when you actually got down data from 60K to 35K, and the recall went up from 61 to 85%. And there was that's like a 41% reduction in data and still a 32% improvement in accuracy. So that was quite counterintuitive, but that's the result I think we have seen training the data. So like, what was the learning from that? Can you walk us through when you said the internal team has created some data set to train on? Was there like a specific kind of data set you wanted to create? Was there some idea of, okay, this is something that the model is not getting it right, so we have to train it on a particular set of parameters, or have to use some loss function? Can you walk us through the dataset strategy?
Sure. So this was like a big learning moment for us. So like when we reviewed the 60K dataset, right? Like a lot of images were distorted and noisy, poorly labeled, and some of them like didn't contain the features that we actually needed. So instead of adding more data, we we filtered out the data aggressively, and then we multiple times validated the data. And then so instead of adding more data, we reduced to the smaller amount of data, but with good images and proper annotation. So once the noise was gone, the model learned the right patterns, and the model became much faster. So precision, as you said, that from the docs, that is 74% to 90%, I guess
the recall value is.
Yeah. And then recall also improved by 15 to 20%. So we learned that the clean and relevant data beats the large noisy data sets, right? Especially for applied computer vision. So it will improve the model's understanding level. So we focused heavily on edge cases also, like complex roof geometries, shadows, trees, occlusions from the vegetation, and satellite images. So one of the challenges for this AI roof generation was the image quality, right? For some areas from the Google map itself, if we see, so Google does not cover very high HD quality images for some areas. So those areas are kind of tough battle for us, because for those images we need to do some upscaling also, so that the image is kind of clear for the model to identify the features, because the training data set is quite clear from our side. but we have also added some like noisy data for the models to understand better. Like for some examples, we have a few locations from many areas where the images were not that clear. So we did that intentionally so that models does not like get monotonous with the data and has a vast vision to get see the data set and like give prediction more better. So yeah, that's how we tune down the data set.
Yeah. So even though we had a good data set where the image was clear, we had to intentionally introduce some kind of blurry because the real world images are blurry. So that we had to train that data to make sure that that works. And I think the complex roof shadows, low quality imagery, some rooftop where there is some kind of shadow on it, we had to intentionally add so that our model can learn and do well in the real life situation. Got it. So it's now in production and multiple companies are actively using it. So what does the current production monitoring look like? What are we doing after we've released it into production?
So right now, as you said, the model is live and companies are using it. So also we have introduced some kind of integration where we like monitor the prediction confidence, like failure patterns and the user feedback. So we have integrated the user rating, right? So for every design that in our platform clients are designing, right? So we after the AI run is made, we just give the user a card which like is about getting the feedback from the user that whether the detection made is good or bad. So we give a 0 to 10 rating, right? And then we record that rating and we record the designs. So with that filtered, we get the dataset from there, and then we try integrating that again into the training pipeline. So this is kind of a reinforcement learning thing, but not fully fledged implemented way. But we are trying to inculcate that properly inside our training pipeline so that we directly can like automate the pipeline.
Got it. So right now it's more manual. We're just trying to see which model, where the model is not really performing better and training with that particular. But later we just want to automate that. Whenever we get a lower rating, that will automatically get added to the dataset and get trained on.
Correct.
Got it. So before we jump into the actual demo, let's talk a little bit about you. You have been at Arca for 4.5 years, and you made the transition from a 3GS developer to now an ML engineer. So how has the journey been, and any lessons you want to share with someone who's wanting to make that transition?
Okay. So like in Arca, like it's my experience has been very organic. So like I started with 3D visualizations, and which actually helped me a lot, like working on spatial and vision-based problems. We had many challenges. It was sometimes challenging, and we had to like follow many algorithmic pipelines and flows to implement many features. So those were very motivating and challenging. So that helped me really push through my limits and then excel on those areas. Then I got opportunity to work on the internal features, like for example, Power Patio and gazebos. So the 3D modeling was taken care, and then I landed on to like working with AI/ML requirement to our product, where we needed to automate the detection process, where the users will like really save time, and it will be a like very good feature to give my contributions to. So I really showed my tendency to like tackle those situations, and then I learned from that. So many things were hands-on. I tried hands-on learning things, so like model training and etc. Like filtering the data set, cleaning the noises and etc. So those were a part of me getting into this AI/ML part. I did not like directly jump into the learning part, right? I just got hands-on, and my seniors really helped me like to get aligned with this and catch it very fast. So also like we don't need to switch like overnight or in a week or month. It takes time, and like we can start by solving real problems and not just learning theory, and working closely with the production systems and understanding the data deeply, and like iterate a lot. So that will really help us to like excel in this. And this field AI/ML has no limits, so we must push our best to follow that.
Yeah, so rather than just taking any course, you would advise the people to take a project, take some time with it, understand the data, and just iterate on it. That's the best way to learn than taking any theoretical course. Got it.
Exactly.
Yeah, let's just dive into the demo now.
Okay. So I'll just share my screen. hope my screen is visible to you.
Yes, I can see this.
Okay. So as you know, this is our software page where we land inside the studio. So this is our base image where we do the designing, and you can see like medium to complex roof over here, right, which has kind of extensions and dormers. So like to design this site, like the user needs to use various tools that we have given. So these all are the manual tools that we have integrated in our studio. So like we have this pen tool feature which works with the Google 3D. Like Google 3D is something we have integrated from the Google photorealistic tiles, and also we have integration of Solar API. So both can be used from here. So currently we are going with the Google Solar 3D process. So to design this roof, so the user has to manually, draw each roofs, right? Each faces accurately. So this will actually take a lot of time to design and complete the whole process. So to eliminate this, we have just introduced this quick pitch to feature. So this is the AI thing that will let us have the roof in seconds. So I think I'll just show you what this button will do.
Correct. In the background, can you let us know what exactly is happening? What's the...
Okay. So, yeah. First of all, we'll take this image and then we filter this image and check whether it has proper roofs or not. And then we pass this image to our upscale model. So the upscaler model will upscale the image and make the features more clearly visible, right? And after that is done, then we land to our roof detection and roof segmentation part. So after the roof is segmented, we do the face detections, and after the faces are segmented, we then calculate the 3D data and 3D mapping of these faces. So the 3D height matches properly, and then it is followed by a few more models, that is obstruction detections and vegetation detection. So the vegetation detection is something that we are working on right now and that will be live soon. So right now I can show you these are the predictions from our AI. So they are the obstructions and this is the final roof that we have got. So I'll just quickly switch into 3D and show you the roof. Yeah. So this is our Google Solar LiDAR data. So we can toggle it on and off from here. So if I hide this, so we can see the predicted roof in 3D.
So the user doesn't even have to match the height. We're already matching the height with the available LiDAR data also.
Yeah, because we had turned on this Google Solar data, so it has auto-fitted. If you want to show me that how we can do that, I'll show you. So we have turned on the Google Solar data. So this is the LiDAR data that we show on 3D, and there is a button called auto-fit to 3D data. So when we click this, so the auto-fit happens, and the model is properly fitted with the 3D data here. So as you can see, there will be minor fluctuations in the mesh over here that is properly intersecting with the 3D actual data of the roof. Right? We can anytime toggle it off and see the actual 3D data here. And I'll just show you the normal roof that is being detected.
Got it.
So the main motive is to have clean faces for panel placement. Yeah, so this is the final roof output from the AI.
Yeah, in future we're adding vegetation also, so later the user doesn't have to care about the trees around it, because we'll be able to design that also. So we'll be having the exact right generation values, because we'll be able to take into account the shadow from the obstructions as well.
Yes, correct.
Okay. Awesome. Thank you, Ankit. Thank you for the demo. That's a really cool feature. So if you are a solar company that is thinking of taking a new software, so Ankit 360 platform right now is equipped with the AI roof feature. So it will help you reduce the amount of time it takes you to generate PV plan if you're a designer, and if you're a person who is trying to just generate proposal with 3D layout, it will reduce the time 15 minutes to 15 seconds, so you can try it out. Thank you.